Okay, welcome everybody to the seminar of our network, EM-QCD. So today we have the pleasure to have Koichi Hattori talking to us. Thank you very much, Koichi, for accepting the invitation, especially that we have this very large difference in time. So in China, it's already 10 p.m. So I really appreciate your presence. So let me briefly introduce Koichi. So he did his bachelor in Keio University. He finished in 2005. He did master and PhD at University of Tokyo, finishing PhD at 2010. And then he did a few postdocs at KEC, or KK, at Yonsei University, RIC and BNL, where he was also later a visiting researcher, also at Fudan University. Then he was a research assistant professor at Kyoto University. And since last year, he's a tenure track research professor in China at Zhejiang University. I hope I have pronounced it well. And he also got the Young Scientist Award of the Physical Society of Japan in 2017 for the work Vacuum birefringence in strong magnetic fields. So I believe that all of us know him, if not in person, like I don't know him in person, but certainly his work. And today he'll be talking to us. Please, Koichi, microphone is yours.
Okay, thank you very much for kind invitation and introduction. So today I'd like to discuss the competition between magnetic catalysis and QCD Kondo effect in strong magnetic field. So this talk is based on this paper we submitted last year. Okay, so let me start. So basically, I discussed a chiral symmetry that you all know that that chiral symmetry is important symmetry in hadron physics, nuclear physics, or particle physics. So this is very fundamental symmetry proposed by Nambu and Jonah Rashino. And this is a well-known QCD phase diagram with temperature and baryon density or quark density. So the symmetric phase was successfully realized at LIC and LHC. And also it is important to note that there are lots of precise data from lattice QCD simulations, zero baryon density at least. And moreover, in recent years, there are some developments at a finite density as well. So in this talk, I'd like to focus on the QCD phase diagram in the presence of strong magnetic field. And there are lots of very interesting numerical data from lattice QCD collaborations in the presence of magnetic field. So there's no sign problem induced by magnetic field. So that's why people was able to provide lots of interesting data in the last decade. So this is one of important result for chiral symmetry breaking or chiral condensate in the presence of magnetic field. And this is another important, interesting suggestion by lattice QCD simulation in the last year. So Italian group suggested possible new critical point in strong magnetic field. So in this talk, I'd like to introduce one more ingredient, that is heavy flavor. So heavy flavor number is not large in quark matter, but they can be regarded as impurity. And if we have a small number of heavy flavors as impurity in the light quark matter, that induces a QCD Kondo effect. So I will explain what QCD Kondo effect and discuss the competition between QCD Kondo effect and chiral symmetry breaking in magnetic field. So the key ingredient in this talk is, of course, magnetic field that is partially motivated by strong magnetic field induced by heavy ion collisions. And also, the important theoretical point is large energy degeneracy induced by magnetic field. So this is basically a part of random quantization. So if you have random quantization, each random level have degeneracy proportional to magnetic field strength. So here, there's an analogy between the systems in a strong magnetic field and high density in the presence of large Fermi surface. So I will discuss this analogy later. And because of this analogy, the chiral symmetry is always broken in the presence of strong magnetic field. That is actually the analogy to the BCS theory at finite density. And then I will introduce heavy-quark impurities that induces Kondo effect. Actually, Kondo effect is also induced by excitation near the Fermi surface, and there's still an analogy between the systems in strong magnetic field and finite density, and therefore both effect induces a Kondo effect. So basically, Kondo effect is also induced by a strong magnetic field. That is the main topic of this talk. Okay, so let me start with the brief introduction to chiral magnetic catalysis, and that is a chiral symmetry breaking in magnetic field. Those people initiated investigating the chiral condensate in strong magnetic field long time ago. And they found chiral condensate increases in strong magnetic field. And moreover, what is important is that in 1995, those people pointed out that chiral symmetry is always broken in magnetic field, no matter how small the coupling strength is. So as long as there's attractive interaction, the chiral symmetry is always broken, even in weak coupling theory, like QED. So as pointed out in their paper, actually this statement is in a cross analogy with the BCS theory. So the original BCS paper already stated that the superconductivity occurs with an infinitesimal attractive interaction. So later, the Polchinski also investigated this statement with renormalization group analysis. So I will basically use RG analysis in this talk, in the first part of this talk. Okay, so what is the analogy between a finite density and magnetic field? So actually, there's a dimensional reduction, both finite density system and also system in strong magnetic field. So of course, if you have Fermi surface, there's energy degeneracy on the Fermi surface. And if you imagine the large Fermi sphere, then there's energy cost only for the excitation normal to the Fermi surface. So at high density, basically the curvature of Fermi surface is vanishing. Therefore, there's a degeneracy of energy level on the tangential plane to the Fermi surface. And there's a similar degeneracy in magnetic field. So this degeneracy basically comes from the fact that there's no preferred position in the transverse plane. So you can put your cyclotron orbit at any position in the transverse plane, and they are all degenerate. because there's no preferred position in constant magnetic field. So in both cases, the degeneracy is two-dimensional, and energy cost is only along magnetic field or perpendicular to the Fermi surface. So the kinematics is basically 1 + 1 dimensional. That is lower than the usual 3 + 1 dimension. So this is the dimensional reduction. And because of low dimensionality, any attractive interaction induces the bound states. So that is the Cooper pairs in case of superconductivity. And in case of chiral symmetry in magnetic field, that is chiral condensate. Okay, so speaking of particle pairing, you can consider not only electron-electron pairing, but also electron impurity pairing. That actually induces Kondo effect. So in 1964, the Kondo was able to explain the anomalous increase of resistance with respect to temperature. So usually resistance monotonically decreases as you decrease temperature. However, it has been known that that in some kind of alloys, resistance goes up at very low temperature, and there's a minimum of resistance at some temperature. So this was actually a long-standing mystery in condensed matter, and in his paper, he clearly pointed out what would be the necessary ingredient to explain the presence of this minimum. That is now called Kondo effect. So he said we need Fermi surface that induces a dimensional reduction, and also we need quantum effect from loop diagrams. And that is basically why this temperature, the position of minimum, is small temperature. So we can have a Kondo effect only when the thermal fluctuation ceases at low temperature. And the most important and interesting part is that he said this minimum can be explained only when, or this minimum appears only when we have a non-abelian interaction. And in his case, non-abelian interaction comes from spin-spin exchange interaction with Pauli matrices. Okay, so now based on this observation, several years ago, we proposed QCD Kondo effect. So we considered heavy-quark impurity embedded in light-quark matter. And of course, we have color exchange interactions between heavy-quark and light-quark with Gell-Mann matrices. So Gell-Mann matrices, of course, non-abelian matrices. And in this context, the Kondo condensate means that the pairing between heavy quark and the light quark in the presence of quark matter. So in the first paper, we discussed the QCD Kondo effect at finite density QCD or high density QCD. And later, based on the analogy between high density system and in magnetic field system, those authors propose that actually Kondo effect is induced by magnetic field without a Fermi surface. So, okay, so let me explain what is the Kondo effect. So I will explain the case of finite density. So basically, it is the same for magnetic field because of analogy. So the setup of problem is the following. So we consider the interaction between light quark field and heavy quark field. So this is effective for Fermi interaction, but between light and heavy fields. And G is effective coupling at the scale of lambda. And what we are interested in is how this effective coupling evolves when you change the energy scale lambda. So we reduce the lambda scale of lambda to Fermi surface. So basically, we reduce lambda to 0, and we will see how effective coupling evolves. So we used renormalization group analysis. So we basically compute the scattering amplitude between light quark and heavy quark. So this is just the reading of the diagram, that is one gluon exchange diagram. So there's nothing special at this moment at the classical level. So we look into quantum corrections. So before doing explicit loop calculation, it is very useful to look into scaling argument. Because it doesn't require a complicated diagram calculation. So later we can move on to explicit calculations. Okay, so, as I already mentioned, there's a dimensional reduction near the Fermi surface. So if you apply low energy effective theory in high density system, that is basically one over chemical potential expansion, you find 1+1 dimensional dispersion relation. So you just expand your Dirac kinetic term by 1 over mu. So this is 1+1 dimensional dispersion relation, and L parallel refers to the momentum normal to the Fermi surface, and L path is a vector on tangential plane. But basically, L path is just a label of degenerate state, so it doesn't appear in this dispersion relation. So this is the manifestation of energy degeneracy. And suppose you compute the loop diagram, then you would have loop integral measure in this way. And if the spatial dimension is effectively reduced to 1, then you don't have this suppression factor in IR domain. So this means the IR dynamics enhanced, and which induces non-perturbative physics like Kondo effect and superconductivity or chiral symmetry breaking. So based on this dispersion relation, let's look at scaling dimension. So we reduce the energy scale to the Fermi surface. So we reduce epsilon by delta epsilon. And accordingly, L parallel is also reduced. However, L path is invariant because it's nothing to do with dispersion relation. And now we determine the scaling dimension of light-quark field, requiring that the action for the kinetic term is invariant under the scaling. So we just basically count the dimension. So we have two light-quark field. So we assume the dimension is, or we denote the dimension deep psi. So we have factor of 2 because we have two fields. And dt is inversely scaling. So we have -1, and dl and dt is scaling with energy. So we have +2 here. And it turns out that the scaling dimension of light-quark field is -1/2.
Sorry, Kyoshi, what's the sub-index plus in the field mean?
This one?
No, on the fields.
On the field.
Psi plus. What does the plus mean?
Oh, plus. Oh. Plus. Oh, okay. So I didn't explain this. So plus is just a projection to the particle state. So because you have particle and the whole state. So basically, this class comes from 1 over mu expansion. So in this expansion, I just projected to the particle state.
Okay.
Okay.
Thanks.
Sorry, I didn't explain it. But basically, this is not important in this discussion. Okay, sorry, I should have realized this. Okay, so we determine the scaling dimension of light-quark field, and we can do basically the same for heavy-quark field. And it turns out the heavy-quark field doesn't scale in a large mass limit. So this is because heavy-quark is introduced as a scattering center, heavy scattering center. Therefore, a heavy-quark looks the same all the way through the RG evolution for light quarks. So it is just a heavy scattering center. So we have those two scaling dimensions. And now we examine whether interaction term between light quark and heavy quark fields marginal operator or irrelevant or relevant operators. So we just insert those scaling dimension to this one. And it turns out the scaling dimension of for Fermi interaction between light and heavy quark fields is marginal. So this implies that if you compute the loop diagram, you will get logarithmic corrections. So we are very confident to move on to the loop calculation. We would get any kind of or the logarithmic quantum correction. But the question is whether the coefficient in front of logarithm is positive or negative. Depending on the sign of logarithm, you will get enhancement or suppression of effective coupling. So the sign is important, and you need to compute loop diagram to determine the sign. Okay, so we look for the logarithm from the loop calculation. And next to leading order, we have two diagrams. One of them is box diagram. So here I have light quark scattering of heavy quark. So we put the kinematics of light quark field on the Fermi surface, and it scattered to some higher state in the intermediate state and comes back to the Fermi surface. And there's another diagram. So in the intermediate state, we have Hall state. So here we have annihilation of particle and the Hall state, and here we have a creation, pair creation. So there are two kinds of process. And we integrate over loop diagram with respect to the since shell from lambda to lambda minus delta lambda. And that gives you log of lambda. So this is what we were looking for. And this is what is suggested by scaling dimension. And there are residual two-dimensional integral that just gives you a density of state. Well, it is basically the surface area of Fermi sphere, which is proportional to mu square. So if you compute those two diagrams, you get a logarithm.
Just a quick question. For the light quarks, you consider zero mass or small mass comparing to what?
We consider zero mass.
Zero mass. Okay.
We assume chemical potential is large. So,
okay, thank you.
Mm-hmm. Okay, so we get logarithm from both of those diagrams. But actually, those log correction completely cancels out without further difference between those two diagrams. So intuitive understanding is important. So in this diagram, we have a particle state in the intermediate state. Therefore, loop diagrams, loop integral approaches to Fermi surface from above that gives you plus sign. And here you have Hall state, Hall contribution. Therefore, loop momentum approaches the frame surface from below. That gives you minus sign here. So for example, if you consider just QED, there's a complete cancellation. I mean, nothing's left. And that's why we need a non-abelian matrix to have a Kondo effect. And if you have color matrices, there are slight difference between those diagrams. So here we have TA, TV, and here we have TV first and then TA. So there's a difference in ordering, and this ordering is important because it's non-abelian matrices. So there's a difference. And if you apply Fields transformation, you can pick up the difference. So those two terms are the same, exactly the same, but you have one different term. And basically, this term contributes to the Kondo effect. Okay, so we found a logarithmic correction from those two diagrams, and then you can construct RG equation. So this is the effective coupling at scale lambda, and you have corrections. That gives you the effective coupling at slightly lower energy scale. So you just write down this equation that gives you RG equation. And what is important is you indeed find a minus sign here as a result of explicit calculation. So beta function is minus. Therefore, we have blow up of effective coupling if you reduce the energy scale to Fermi energy. So there's a random core where effective coupling diverges. So this is analogy of QCD scale, where we have divergence of QCD coupling. So this scale is called Kondo scale. Basically, this scale provides the location of minimum of resistance. So this Kondo scale basically provides a temperature scale. Okay, so because of strong coupling nature, the resistance is increasing in low temperature. So this is the non-perturbative physics, actually. Okay, so after our paper, there are several developments by several authors. So I just like to mention nice papers by those authors. Okay, so summarizing so far, we discussed analogy between finite density and in magnetic field. And in case of light-quark pairing, we have superconductivity and magnetic catalysis of chiral condensate. And next, I discussed QCD Kondo effect at the finite density with RG analysis. And because of analogy, those authors pointed out that Kondo effect is actually induced without density, but by magnetic field. So this is it. And okay, so far we discussed analogy between those two systems, but now I focus on, from now on, I focus on the dynamics in magnetic field and discuss a competition between magnetic catalysis and QCD Kondo effect induced by magnetic field. So basically, the issue is the following. So we have seen that magnetic catalysis inevitably induces the formation of chiral condensate, and Kondo effect inevitably induces formation of Kondo condensate, that is heavy-quark and light-quark pairing. So this is is similar to the episode in ancient China that is called spear and shield. So this weapon Martian is advertising his strongest spear in the world. So he's saying that his spear is strongest. But at the same time, the same guy is saying that his shield is the strongest in the world. So people are wondering which of them is indeed strongest. So the issue is similar. So we would like to investigate which of magnetic catalysis or condensate Kondo effect is stronger. Okay, so for demonstration, I used the simplest model. So I just consider one light flavor and one heavy flavor with N colors. And this is my model Lagrangian. So this is a kinetic term for light-quark field in magnetic field. So basically, I just pick up a lowest random level, and this kinetic term is already 1 + 1 dimensional. So parallel refers to the direction of magnetic field. And this is kinetic term for heavy-quark field, and I applied 1/n expansion, 1/heavy-quark mass expansion, and I just pick up leading order. And at leading order, we just have zeroth component here. And those two are interaction terms. This is light-light interaction, which induces chiral condensate. And this is heavy light interaction that induces Kondo effect. And GLL and GHL are effective coupling between light-light and heavy light quarks. Okay, so we applied mean field method. So we introduced a chiral condensate as always. So M is basically the chiral condensate, magnitude of chiral condensate at mean field level. And here we also introduced mean field for Kondo condensate. So this is kind of new thing here. And after introducing those two condensate, you can exactly diagonalize the Lagrangian, mean field Lagrangian. So we have basically 4 modes because we have particle and antiparticle of heavy and light quark fields. So we have 4 modes. And once you get the eigenmodes, you can compute thermodynamic potential. So this is the vacuum term. Basically, this is vacuum energy, and this is final temperature contribution. And what is important is you only have one-dimensional integration measure. So BP is momentum along magnetic field. So this is a consequence of dimensional reduction. And because of this reduction, we get a logarithm. So again, we have logarithm in mean field analysis as well. And because of logarithm, the potential profile looks like this. So this is the schematic picture of potential profile with respect to Kondo condensate and chiral condensate. And this potential is always convex upward at the origin because of this logarithm. So if you approach the origin, you always have enhancement due to the logarithm or singularity, actually singularity at the origin. So therefore, always non-zero condensate is favored at 0 temperature. And if you include finite temperature contribution, this term also provides logarithm, but with opposite sign. So this final temperature contribution cancels the logarithm at the 0 temperature. Therefore, you can have a symmetry restoration at final temperature. And you can see the same thing with gap equation. So gap equation is obtained from stationary condition that is given by derivative of thermodynamic potential by the condensate, Kondo condensate and chiral condensate. So we get the coupled equation, coupled gap equation. So this is for chiral condensate and this is for Kondo condensate. But they're coupled because of this argument of logarithm. This has a little bit complicated structure. And if you just look at magnetic catalysis and Kondo condensate separately, you can analytically find a non-trivial solution. So here you turn off delta, you put delta to be 0, and you can solve just this equation. And because logarithm sweeps from 0 to infinity, you always find intersection between right-hand side and left-hand side. That is a non-trivial solution. There's always non-trivial solution at non-zero m. So that is the result of magnetic catalysis. And you find the same structure for Kondo condensate. So if you put m to be 0, you get the Kondo gap equation for Kondo condensate, and also always the non-trivial solution. That is also given by this exponential form. Okay, so now I move on to the main result. So we numerically investigated the global minimum of effective potential that gives you the condensate in the presence of competition. So this is the result at 0 temperature, and red line shows the chiral condensate, and blue line shows, sorry, opposite. Red line shows a chiral condensate, and blue line shows a Kondo condensate. And without competition, we get the dotted line, the dashed line for Kondo condensate. So the difference comes from light-quark mass. Sorry, here, okay, previously in RG analysis, we assumed the massless limit, but here in near-field analysis, we investigated both of them. So the dotted lines for massless limit and dashed lines for finite current quark mass. And the order of phase transition changes. So in case of massless limit, we have a smooth connection, but for finite current quark mass, we have a second order transition in the absence of competition. And if we have both chiral condensate and Kondo condensate, we get the final result shown by solid lines. So when we are in the weak magnetic field regime, basically Kondo condensate overwhelms Kondo condensate. So we so here Kondo condensate is always 0, but you have increasing chiral condensate. But something interesting happens here. So there's a critical magnetic field strength where Kondo condensate starts to grow. And once Kondo condensate starts to grow, chiral condensate saturate at some value, certain saturation value. So this is one of our main results at 0 temperature. So actually there's a turnover between the vacuum dominated by chiral condensate and the vacuum that allows for the coexistence of chiral condensate and Kondo condensate. So this is a new quantum critical point because the a transition occurs at 0 temperature. So that is a quantum critical point. Okay, next we introduce final temperature effect. And again, red line shows chiral condensate and blue line shows Kondo condensate. And now horizontal axis is temperature. And basically, pursued transition temperature of chiral condensate is higher than Kondo condensate because it's a crossover transition. Therefore, it doesn't, the transition occurs just gradually. That's why we have a higher TC. But for Kondo condensate, we have a singular transition here, somewhere here. And when we have competition, Kondo condensate is subject to a first order phase transition, shown by blue line. And what is very interesting is that actually chiral condensate increases as you increase temperature. So this is very anomalous behavior. And this is the signal of the presence of competition. Because of Kondo condensate, this increasing behavior is induced. So actually, this is the signal of the end of competition. So because the Kondo condensate disappears at this temperature, the chiral condensate is released from competition. And that's why chiral condensate can increase as you increase temperature. So this is one of the signature for the end of competition. Okay, and to determine the order of phase transition, so we investigated those 3D plots. So this is Kondo condensate, chiral condensate with respect to temperature and magnetic field. And this is Kondo condensate with respect to T and B. But just please be careful the direction of axis. So here we have temperature in this direction, and here we have temperature in this direction. So we had to rotate the 3D plot to show this structure. So if you have the same direction of axis, actually this structure goes to the back of plot. So we had to rotate, although this is kind of confusing. So okay, so here we have saturation of chiral condensate at a strong magnetic field, and at finite temperature we have first order transition in the direction of increasing magnetic field, and we have the basically correlated structure in Kondo condensate as well. So based on those numerical analysis, we extracted this phase diagram. So this is a phase diagram with respect to magnetic field and temperature. And we found a second order quantum critical point at zero temperature. And this critical point is connected to the first order phase transition line at a fine temperature. So in this regime, the vacuum is dominated by chiral condensate, non-zero chiral condensate, and we don't have Kondo condensate. But on the right-hand side, we have both chiral condensate and the Kondo condensate. Actually, Kondo condensate dominates over the chiral condensate. So those two phases are separated by first order phase transition line. Okay, so this is our main result, and now here I come to my summary. So we investigated the QCD phase diagram in the presence of heavy-quark impurity that induces the Kondo effect, QCD Kondo effect. And at zero temperature, we found saturating behavior of magnetic catalysis in strong magnetic field. So this is anomalous behavior because we know that without Kondo effect, the magnetic catalysis always increases with magnetic field. So this is one of signature of the presence of Kondo effect, the competition with Kondo effect. And at finite temperature, we also found anomalous increase of chiral condensate as you increase temperature. This is the signal for the end of competition. And there are a few outlooks. Of course, it is very interesting to investigate the competition with lattice QCD simulation. So this is basically static thermodynamics. And if we try to apply our work to experiment, we need to compute dynamical quantities like transport coefficients. And also, what is interesting is application to Dirac symmeter or wire symmeter in condensed matter system. They also have relativistic dispersion relations. Okay, thank you very much for your attention.
Thank you, Koichi. Thank you.
Thank you.
A very nice presentation. So now I will open for questions. Christian?
Thank you, Kiyoshi, for the presentations. Very interesting. When we talk about this is a very high density scenario. We are talking about the neutron star core.
Just a comment. Maybe if you want to get out of full screen now, so you can see
okay.
faces of people.
All right.
Okay.
Yeah. Okay. How dense must be such kind of system? If we're talking about QCD, it must be a neutron star core.
Yeah. So we are also interested in neutron star core, but one issue we need to make sure is the presence of heavy quark. So we could have a strange quark maybe in neutron star core. But we need to make sure the origin of heavy quarks in neutron star core. That is, I think.
Oh, I see.
Yeah, we need to make sure that it.
Yeah.
So it's not so easy, I think.
And my second question is, well, you calculate with the normalization group the behavior of the coupling with the scale, but is this theory normalizable? This kind of coupling between the heavy and light quarks, the Lagrangian is still normalizable with this four.
So here we are not interested in UV regime. So we are going down to IR. So I think the UV renormalizability is not the issue here.
Okay.
Yeah, but basically we use Fourier interaction. Therefore, if you go to UV regime, I think it's not denormalizable.
Okay. And what do you expect if quarks couple with the other heavy particle, not necessarily a heavy quark, it would behave similar like this, or would you expect something different? Or if it is possible.
You mean like kind of heavy hadron or heavy?
A baryon, for instance.
Oh, okay. I think that's possible, and it depends on whether we have no-abelian interaction or what kind of interaction at the hadron level. Actually, my collaborator investigated such interaction.
Yeah, but the interaction must be non-abelian.
Yeah, sure. Yeah.
Okay.
So, for example, my collaborator discussed D meson in New Korea matter, if I remember. And I think the conclusion was there is a similar effect. So, yeah, I think you can expect a similar result.
The similar results. Oh, okay. So it's possible with neutron stars.
Oh, I see.
Quark stars, maybe.
So if we have nucleon
well, there are some cores that are expected to be a mix between quarks and hyperons also. So.
Yeah, I think that would be interesting. Well, what about the interaction between electrons and the protons?
Oh, yeah.
Proton, there are not many protons, but hmm. Yeah, it's interesting.
Okay. Thank you very much.
Thank you.
Okay. So, Giorgio?
Hi, thanks for a nice talk.
Thank you.
Just wondering. I mean, at the LHC,
Mm.
you have 50 to 100 charm quarks per event.
Mhm.
Varies a lot. I mean, from what I understood, you have a low temperature. Could there be any LHC related phenomenology? Could they act as impurities?
Mhm. Yeah, I was interested in, um, yeah, for example, so I was interested in heavy-quark diffusion dynamics in LHC or uh, leak. So we could, if we have a strong magnetic field, we could have some effect that is reflected in the diffusion dynamics. But yeah, but we need to make sure that the magnetic field strength is larger than the temperature scale. I think that is the condition.
Okay, that's not going to happen. I see.
Mm.
Yeah, that's
Mm.
likely not going to happen, right? Thanks.
It's a little bit tough. Mm.
Norberto? Norberto? You're mute.
Yeah.
Okay.
Okay, fine. Well, thank you very much for your talk. The phase diagram that you have shown were done at fixed values of the coupling constants. How did you fix this coupling constant, and
Oh,
what happens if you use, another value for the coupling constants?
okay. Actually, we didn't fix the coupling constant. So actually, this result depends on only the ratio
Okay.
between coupling constant and cutoff. So this is also a result. This is also a consequence of dimensional reduction. So you can normalize all the quantities by one quantity. So
Okay, fine.
yeah.
Good. But how do you fix this ratio then?
Oh, so this is just for illustration. So we tried some parameters, but basically the result is the same. So
Okay.
yeah.
So is there some critical ratio for which this situation changes, or is always the same?
There's not the critical, but actually relative magnitude between GLL and GHL matters.
Mm-hmm. Yeah, what I mean is, what happens if this relative magnitude changes, and is there
Okay.
some
Yeah.
particular
So
value for which situation is very different, or something?
yeah, for example, if you have a much larger GLL than GHL, that favors chiral condensate
Mhm.
as a tendency, because GLL induces basically chiral condensate, and the GHL induces Kondo condensate.
Good. But there might be some ratio for which, for example, only one phase appears. It could be,
Okay, yeah, basically, when GLL and GHL are the same,
Mhm.
Chiral condensate and Kondo condensate degenerate.
Okay. Good.
Okay, maybe that is what you say, critical coupling.
Now, what I mean is that, for example, if the chiral coupling, say, is, I don't know, 10 times the other one, then the Kondo phase doesn't appear at all. Could be. I mean,
Yeah, we didn't check extreme cases.
Okay,
Yeah.
good. Thank you.
Thank you.
So just before passing to Fernando, just continue the question from Norberto. Just a second, Fernando. So you don't know if there is a critical coupling for which you don't have the Kondo phase anymore. That's what you mean, right?
Right, basically. It also depends on actually the current quark mass. Because current quark mass basically favors chiral condensate because of explicit breaking. So there's a balance between those two, the mass effect and the coupling effect.
Okay, so go ahead, Fernando.
Hi, thanks for the nice talk. I just
Thank
want to know, how do you control the amount of impurity? Is there something like a chemical potential for the impurity or a control over the densities? How do you do that?
Yeah, that's a very good question. So, right. So we can introduce the chemical potential for heavy-quark field, but here we assume a heavy-quark field has a zero chemical potential. That just means that we have the even number of heavy-quark and anti-heavy-quark.
I see. Okay. But I understand that when you study Kondo effect, there is you have to limit the amount of impurity. So it cannot be anything, right? Otherwise, this would spoil the description. So you have to still keep the light quarks. They have to be much more numerous or more dense than the heavy quarks.
I think in this case, so especially at zero temperature, so we basically we consider zero temperature case in vacuum. So I think in that case, the heavy-quark field is also the fluctuation in vacuum.
Okay, so just one last remark is coming back to Christian's question. It will be very interesting to study this effect in stars in a system at low temperature and high density. And there we have the problem of, as you said, to guarantee the existence of charm quarks, because charm quarks in stars, they can easily decay and go away. There's nothing to prevent them to disappear. But so still, what's your opinion on that? So you just said that we have to be sure that the charm quarks are there, but what is the prospect of having this in stars? Or have you thought about this? Or not even in stars, but in heavy ions, in the situation where you have not such a high temperature, but large density, as some experiments are planned to do that in the future at FAIR or NICA or other machines.
So in my personal perspective, I'm rather interested in heavy ion collision at low energy. That could induce both dense system and heavy-quark impurities. I think that is rather promising compared to neutron study.
Good. Okay. Thank you.
Thank you.
More questions? I have a final question. So you mentioned in your last slide that you could apply it to condensate matter, this Dirac system. So in this case, what would play the role of a heavy flavor? Because in Dirac materials, the quasi-particles are massless, or they have very small mass. So what could be the heavy flavor in this case?
Right. So that massless dispersion relation corresponds to light-quark field in our case. They could have really impurity. Right. Originally, in condensed matter physics, they have real impurities. That is basically, dope
And then
impurities.
the impurity couples to your quasi-particle, something like that.
Right. Impurity couples to basically massless excitation. That is more similar to the original Kondo as well. The Kondo considered coupling between conduction electron and the impurity.
Mm-hmm. Okay. Okay. Thank you very much.
Thank you.
I will stop recording now.
Mhm.